Physics is a fun time. Okay, so the next question that we got on the menu today is we're asking for the relationship between potential energy and kinetic energy. Okay, the first thing I want to mention about this is the law of the conservation of energy. Law of conservation of energy. You know what happens when you break this law? Nothing, because it's impossible to break this law. Ha, trick question. So the law of conservation of energy is saying that the total sum of energy in a system is always constant. Or, in other words, energy cannot emerge from nowhere. Energy can only be transferred never spontaneously made. Okay, so basically, we can put this as an equation, like energy of system is equal to the potential energy, so E potential, plus E kinetic. Okay, let's make an example out of this. Okay, let's say I'm throwing a basketball up in the air and then I'm going to catch it. Okay, so the system is the ball, but only after it touches my hand, or after it leaves my hand and I'm no longer touching it. That would be the system. Because if it's like while I'm throwing it, well, I'm a part of the system, and that just the ball itself. So a ball flying straight up. So example, ball flying straight up. So initially, it's going to have a lot of, so it's going to follow a path like this. So if here we have like a height, and here we have time, we know that it's going to follow a parabolic trajectory. Now that doesn't mean I'm like throwing it at an angle, like its actual path straight up, and like straight down. I know it looks like it like moved horizontally a bit, but you know, it's not really an easy way to draw two arrows on top of each other and make them still look like two arrows. But yeah, so the actual path is like this. So initially, when it leaves my hand, it's moving upwards with a considerable amount of kinetic energy. We know that kinetic energy is 1/2 mv squared. And potential energy, well, we have mgh. That's gravitational potential energy. Well, I guess since gravity is the only applicable force in this situation, you know, that's the only like potential energy that we need to worry about for this particular example. Okay, so initially, the moment that the ball leaves my hand, let's say that is height 0. When height is 0, h is equal to 0, well, there's no potential energy. But there's going to be a whole lot of kinetic energy because it's flying upwards. But as it flies up, like as it gets higher and higher, it's slowing down. You know, it's not accelerating upwards. It's quite the opposite. It's accelerating downwards, but since its initial velocity is up, you know, it's initially going fast up, but it slows down, and then it's going to hit the apex of the of its throw, or the maximum height, and then it's gonna have to, just for the brief moment, like this could be like a nanosecond, it's gonna have a velocity of 0 just as it reaches the tippity top of its path, and right before it makes a U-turn, it starts coming down, its velocity is gonna be 0. At that point, it's at its maximum height, and v here is gonna be 0 in the mv squared equation. That v is gonna be 0, and at that point, all of the energy inside that ball is going to be potential energy. And then it's going to lose potential energy as it moves down, because as it moves down, it's accelerating. It's going faster and faster. If you ever fell, you've probably experienced that before. So as it goes up, the potential energy increases. So upwards part. PE going up, and KE, kinetic energy, is going down. It's slowing down because we are downwards gravitational acceleration. When we're going downwards, more height is more potential energy. So potential energy, that's going down as we're going down. And kinetic energy is going up. Okay? So, but you can see, because of the constant amount of energy that's in this system, we can say stuff like, if we know at a certain height how much potential energy it has, and we know like the initial amount of energy in the system, we could figure out how fast it is at a certain height. And there are some things that we know that are easy, that is like, initially the moment, just the brief moment that it leaves my hand, no potential energy, purely kinetic. At the top of the throw, purely potential energy, no kinetic, because it has a velocity of 0, just for a brief moment, very brief moment. And then as it's coming down, the potential energy gets transferred into kinetic energy. Okay, so yeah, hopefully that can kind of explain the relationship between potential and kinetic energy. Of course, in this example we used gravitational potential energy, but potential energy comes in many different forms. Like you'll have spring potential energy, like if you ever held a mechanical pencil, like there is potential energy that you have if you're like holding down the spring. Or there could be like chemical potential energy, that's more into like the chemistry side of things. And yeah, many different forms of kinetic energy. For physics, the most important ones are going to be gravitational and spring kinetic and potential energy. Yeah. And energy can also be used in the deformation. So maybe to make this even more clear, like technically there is like a deformation term here. Kind of what the energy of deformation is like, if you push against like a squishy ball, you're not really increasing its kinetic energy by a lot because it's not really moving, but the energy that you're putting into it goes into squishing it. So for this like ball flying up and down on the ground or being thrown up and down, there's no deformation happening, so this gets zeroed out. But in situations where things are compressing, you will have like an energy of deformation, but typically you won't see that unless you're very interested in doing like mechanical design. So yeah, if you're interested in mechanical design, stuff will be quite useful. Because sometimes like for cars, you want them to deform, because like let's say you're driving real fast and then you hit a brick wall, you don't want all of that kinetic energy to be like felt by you. You want your car to deform and absorb some of that kinetic energy, so you're more likely to avoid an injury. Yeah. So the above solution is good. Awesome.